All right, today we are going to be introduced to derivatives through instantaneous velocity, okay? So previously we talked about average velocity. So like what's the average velocity that something went over this period of time? What do you think instantaneous velocity is?
Instantaneous. Added instant.
Okay, yeah, it's instantaneous. It's at an instant. It's like how fast is it going at this exact moment in time? Okay, not an average, but at this exact moment in time, all right? Because honestly, objects rarely ever have a legitimately constant velocity. It's a rarity in the world, okay? So let's look at a little example.
Nothing starts out with velocity.
This is a slightly better example of what velocity might look like. When we did constant velocity, what did the line look like? It was just straight, it was linear. What's this one look like?
It's curved.
It's curved, okay? So, and it's curved because the velocity is changing. So, curved because velocity is changing. All right. So let's look at this a little bit more in depth. Okay, so let's say we're going to look at a tiny little segment of this, and we're going to blow it up over here. Okay. If we were to blow this up, what do you think it would look like?
A straight line.
Yeah. So if you were to blow it up, you would have some sort of straight line. Okay? So let's say that this is this. Okay? And with that straight line, we would have what we're used to with velocity. We would have rise over run, and that would be delta x over delta t. And you guys know how to find the slope of one of those kinds of lines, right? Okay, so this is our very, very small segment at a little point. And like you guys said, it's essentially a straight line. Now, that means that we are going to call this a what line?
A tangent.
A tangent line, okay?
Tangent.
It's me pressing down, trying to go straight, but failing miserably. Okay, so it is a tangent line. And that's just the tangent line blown up. Okay. Yes. Tangents are linear. They have that constant slope. You're exactly correct, okay? Now, as our segment or our time interval gets smaller and smaller and smaller, that's going to make it easier and easier for us to sort of approximate a V average at that exact time, right? So the more zoomed in we get, the more of a linear slope we get, the easier it is to take the rise over run and to get to our final answer. Now, mathematically, what we like to say here is that the limit approaches zero. As we get smaller and smaller, the limit approaches zero. What's all the moaning and groaning for? Are you guys doing limits right now? Which means we're going to say the limit of delta t approaches zero. Okay? Which means when we write this out, if we're saying, like, let's say we're looking for the velocity in the x, we're going to say the limit as delta t approaches zero of delta x over delta t. And what that gives us is dx dt, which is our instantaneous velocity. Instantaneous velocity, and we call this a derivative.
Yeah.
A little dx over dt.
That's instantaneous velocity.
That's a derivative. We're going to talk about what it is more, but the dx over dt, that's our derivative. And don't worry, I'm going to show you guys what a derivative is, how you find it, all that stuff, but that's what we're starting with today. That's how you would find an instantaneous velocity. So I'm going to rewrite this over here so that we can have it at the forefront of our minds. So what have you guys learned about limits so far in calculus?
They get the left side, right side.
Yeah, left side, right side. They have to approach the same point from both sides.
So what basically happens, why it's the limit, is as our delta t gets smaller and smaller and smaller, the average velocity is reaching a constant, or what we consider a limiting value. So we're going to look at this graph now.
It's pretty.
How's everybody's morning going so far?
I'm so tired.
I am also very tired. I feel like today's one of those days where I woke up on like the wrong side of bed.
I woke up at like 2 in the morning. I was so thirsty.
All right, so we're going to look at 3 points here, okay? We've got point A, point B, and point C. Okay. I'm going to make this a little bit more exact. Make it like that. Okay. So, question 1 for you guys, or question A, not in reference to these. These are uppercase. These are lowercase. This is just me saying this is my first question. At which labeled point or points do we see a value of 0 here?
Oh, for the x or the velocity?
For our velocity.
A, C. Or is it? Is this position?
This is position. This is time. Think about it like we're on an elevator, okay? And we're going up and down. Okay? So this is our y-axis. So that's what I'm saying. We're going to think about we're on an elevator. We're going up and down. And this is our time. Okay? So we've got position, time. We're trying to figure out velocity from this. Okay, so C is one of the points. Is there another point? A. Okay, you guys tell me why is it C? Let's start with that because most people said C. How do we know velocity is 0 at C? Yeah, it's a straight line. Okay, those of you who said A, how do you know it's a constant velocity at A? Oh, sorry, not a constant velocity, 0. How do you know it's 0 at A? Yeah, it's a turning point, okay? So at a turning point on a position versus time graph, we can say that we're at 0. Now, at which point or points does the elevator have its absolute maximum velocity? B. Okay, other than the fact that you know it's 0 at C and A, what makes you think that B is a maximum velocity? Not necessarily.
That's when the second is the 0. It was the only other one.
It's the steepest slope we have here, okay? So this is going to be based off of your maximum velocity is going to be where there's the steepest slope. And then C was, what did you guys say was your reasoning behind knowing C was 0?
Or wait, no, C is big.
And what was the reasoning behind A? Turning point. There isn't either. There it is. Okay. Now, let's think about what this would look like if we graphed it as velocity versus time. So we're gonna have to pick this thing apart. We're gonna try and now graph this as a velocity versus time graph. So what's happening right here?
It's going down. The negative. Are you talking about the
We have to pick this apart. We have to draw it as velocity versus time now. We've got to think about it. So what velocity are we at A? 0. Okay, so what's going to happen here is we're going to start down here at a negative velocity because this is a negative or positive slope? Negative. And what did we say when we were looking at graphs the other day? A negative slope on a position versus time graph means about velocity. It's a negative velocity, right? Okay, so we're going to start at a negative velocity until we hit point A, which is at 0, right?
Yeah.
Okay, is this a negative or positive slope? Positive. So we're going to keep going up until we reach some maximum velocity, and that'll be our point B, right? And then we will start, this is still a positive velocity, right?
Yes.
But is it speeding up or slowing down? Slowing down because you eventually end up stopping, so then it would come down here, and then it stays at that 0, which is what that lets us know. So C would be somewhere in here. So negative slope let us know that we had a negative velocity, but we knew that that velocity was approaching 0, right? So we start at a negative velocity, we get to 0, then we have a positive slope, and we know it's going faster and faster and faster until it hits a maximum at B, and then it starts slowing back down to C, or to a stop. So that's the graph transformation. Does that sort of make sense? We'll do more practice with graphs. Actually, Monday, we're doing graphs the whole day, so.
Very fun.
Do we have to draw the graphs or the graphs are
The graphs are drawn. You're going to be doing like a derivative graph, like matching activity. It's a good time. It's a good time. Okay, so now what we're going to do, though, is we are going to talk about derivatives, okay? So, I didn't catch that. It's okay. I wasn't shushing you, I was shushing them. Okay, so calculus. Why was calculus invented?
Find instantaneous. Find instantaneous.
Ooh, okay. It was created to explain physics, but specifically it was created to deal with these types of instantaneous quantities. So not just instantaneous velocity, instantaneous acceleration, instantaneous everything, okay? That's why calculus was invented. And since it deals with instantaneous stuff, it helps us to evaluate the limits of different things, okay? Now, let's consider the function u of t equals c t n, okay? This is the function we're going to be looking at today. Now, c and n are constants, okay? So I'm going to put this off to the side. C and n are constants. Okay, so I'm going to give you guys the formula for taking a derivative. It's going to take Miss Thompson weeks or months to get to once you start talking about derivatives. I'm jumping straight into the shortcut, okay? Okay. because that's what we do in physics. We just jump to the shortcut, okay? So if you have the function of ut of ctn, we would call that, or it would be defined as du over dt. What this means is we're taking the derivative of u with respect to t. So the derivative of the u function with respect to t. Okay, so that's what du over dt means. Now, the way you take a derivative, this is called the power rule, which is honestly pretty much all we use in physics, is this. Okay, you guys watch. We take the n, okay, and we bring it down in front of the other constant. So we have n times c t, and then what happens to the n up here is it would become n minus 1. It'll make more sense when we do it with actual numbers. Okay, but this is our formula that we follow. Do something to mark this because you're going to want to refer back to it a pretty good bit this year. This is our formula. You're going to be using this formula a lot. Okay? So we will look at it with an actual sort of example to what we would be doing in physics, okay? So let's say we have a position function that we're given, okay? We're told that x of t is equal to 2t squared, okay? So this is a position function that we were given. All right? And why might we want to take the derivative of it? What do you think its derivative is going to give us? So the derivative is you are taking, yeah, it's like, so when we're doing the graphs that we just looked at, right? And we took the position graph and we changed it into a velocity graph, the derivative is the slope of something, basically. Yeah. Whereas when we do the integral, it's going to be the area under the curve of the graph. The derivative is the slope of the graph. Okay? So why we use it in this class in physics is because if you take the derivative of position, you guys, what does the slope of a position versus time graph give you? Velocity. So if you take the derivative of a position function, it gives you the velocity function. Okay? So like if we take this derivative, how it would happen is this is our c, this is our n. So we would bring over our n, and we would get 2 times 2, t2 minus 1. Do you guys see how that translates into what we put up there? If this is our c, and this is our n. Okay, and that's going to give us, what's 2 times 2? 4t, and what's 2 minus 1? Yeah, to the first. Do we have to write anything there for that? No. Why do I keep on looking at the regular physics one? It needs to go away. Okay, so what we know now is, what did I say taking the derivative of the position function would give us? So what we have now is that the velocity function with respect to time is 4t. All right, so if we have a value that doesn't change with time, that means that n would be 0. So let's go ahead, and we said that if you take the derivative of position, it gives you velocity, right? When we looked at a velocity versus time graph, what did we say that the slope of that graph gives us? Do you remember? it gives us acceleration. The slope of a velocity versus time graph gives us acceleration, okay? Which means that if we take the derivative of a velocity function, we get what? Acceleration. So if we were to take the derivative of this, the 1 would come down, multiplied by 4, and then we would have t of 1 minus 1. What's 1 times 4 give us? And what does 1 minus 1 give us? 0. So when you get a 0 here, what happens is the t goes away. Because t to the 0 doesn't, it means the t goes bye-bye, okay? So we would be left with that acceleration with respect to t is just 4. So in this case, we would have a constant acceleration. You guys don't worry, we're gonna get so much practice with this. I have days upon days of practice scheduled, okay? Now, something that I would put in my chart or like in my notes if I were you is I would write x, v, a like this, and I would draw an arrow going down and write derivative. Because to get from one to the other, you're going to take the derivative. So to go from position to velocity, you take the derivative of the position function. To go from velocity to acceleration, you take the derivative of the velocity function, okay? Now, what I'm about to tell you would make Miss Thompson's ears bleed, okay? In physics, you mainly, when it comes to derivatives, you need to know two things. You need to know that it's the slope of a graph, and you need to know how to plug it into that little equation I gave you. You don't need a deeper understanding, okay? Is she going to give you a very deep understanding? Yes, she is, and it's going to be awesome, okay? I'm not, because you don't need it for my class. You need to know that it is the slope of a line, and you need to know that this is the way you take a derivative. That's all they expect you to know on the AP exam. They don't ask you to go into an in-depth explanation of what a derivative is. They want you to know its slope and that this is what you plug it into, okay? You sleepy?
Yes.
Okay, now there's one other thing to show you guys that you'll have to do with derivatives. Okay? There's also, sometimes you're going to have stuff added together, okay? And you'll have to take the derivative of two functions that are added together. So you might have to say d dt, so the derivative with respect to time of u, let's say, plus w. So it's like you're adding two functions together, okay? When you do that, you take the derivative of both separately, okay? So you would take the derivative of the u function with respect to t, and then you would take the derivative of the w function with respect to t. And we will be doing an example of that too, yes.
Where's the u function? Like what? How do you get that?
You've given it.
Oh wait, is that a u?
Yeah, that's a u.
Oh, my bad.
Guess I'll be more careful with how long my lines go. Okay, so we're gonna do an example together that sort of brings it all together. And then tomorrow all day you're gonna be practicing taking derivatives to make sure that we sort of get an idea of it. Oh, I also have a date for your guys' test, just FYI, September 2nd. September 2nd is gonna be your first test. Yep,
We go where?
on Labor Day break.
Oh. Is it Friday and Monday or?
It's a half day Friday, then you have Monday off.
So yes, basically.
Probably.
So if you're planning on missing that Thursday, you better be ready to take the test like as soon as you get back on Tuesday. Okay, so a particle's position is given by the function x of t equals negative t cubed plus 3t meters, where t is in seconds, just in case you had any thoughts about if it was in minutes or anything. It's in seconds, okay? And we need to do 3 things. So A, what are the particles' position and velocity at t equals 2 seconds? We have a part B and C too, but we're going to do each part one at a time. So our first thing is, what are the particles' position and velocity at t equals 2 seconds? So let's start with its position. And I'll give you guys a second to get this written down before we dive in. Okay, cool. It's almost you have it written down. Okay, how do you think we're going to have to handle finding its position at t equals 2 seconds? Do we have to do anything to that equation? No, this is the position function. So all we have to do here is plug in what for t? 2. So we would say that the position at 2 is equal to negative 2 cubed plus 3 times 2. So if somebody can type that into their calculator and tell me what they get. I mean, technically, it's not like it really matters. Once you cube it, it becomes negative anyways. All right, is it negative 2 cubed negative 8? Yes, and then 3 times 2 is 6. So what's negative 8 plus 6, you guys? Negative 2 meters, okay? So that would be its position at 2 seconds. Okay, I added back up the little derivative trick over here for the power rule, okay? So we can figure out how to change this position to velocity together. So we're given position of xt equals negative t cubed plus 3t meters, right? So this is when this comes in handy. Do you guys see that we're having to take the derivative of 2 things that are getting added together? Okay. So we're going to say d dt of negative t cubed plus 3t. That's what we're doing right now. That's what we're taking the derivative of. Okay. This right here means that the next thing we're going to basically say is that we're doing the derivative with respect to t of negative t cubed plus the derivative with respect to t of 3t. So we're taking the derivative of each one, and with respect to t means that, right here we said c and n are constants. T is just our variable. So we take derivatives with respect to our variable that's not a constant. Okay? So if we are looking at this and we know that here our c is a -1, we have t and our n is a 3. What would be the derivative of -t3? So we would bring down the 3, right? Times -1 times t, and then 3 minus 1, which gives us what, you guys? What's 3 times -1? -3, and then what's 3 minus 2? Sorry, I mean, what's 3 minus 1? I don't know why I wrote 1 because you guys said it was 2. That's why I did that. Okay, 2. So that would be our derivative of -t³. I know it's going down towards the bottom of the board. I'm sorry, you guys. Okay, and then plus, for this, what's the n we would have to bring over? 1. 1 times 3 times t, 1 minus 1. So what's 1 times 3? 3, and what's 1 minus 1? 0. Okay, so this is what we ended up with when we took the derivative, right? We ended up with -3t squared plus 3. I'll move this to up here so you guys can see better, okay? So we got that the velocity function is going to be -3t squared plus 3. That's what we just found together. Does everybody understand how we got there? Yeah? Okay. So what do we do to find the velocity at 2 seconds? You plug in 2 to where the t's are. So you'd have that the velocity at 2 seconds is equal to -3 times 2 squared plus 3. So what's 2 squared? 4. What's 4 times -3? What are the units?
Meter second.
So at time t equals 2, it's at a position of -2 meters and it's going -9 meters per second. I'm just waiting until I see everybody stop writing, so kind of erase this to go into part B. Do you have any questions so far? No? Okay. What I've found is most useful for students is to just think as this derivative equation as just another one of your physics equations. To not really try and think of it in terms of that it's some sort of calculus thing, but to just think of it in terms of this is just one of my other physics equations that I need to know. That seems to have been what's helped people the past few years. Okay. So part B is draw graphs of x. So we're going to draw the position and function graphs during the interval of -3 seconds to 3 seconds. Okay, so like this could be something, this question that we're actually doing right now, this like 1, 2, 3 parter, this could be an example of some sort of FRQ that they would have you do on the AP exam. Okay, so now we're going to draw the graphs of the time interval during -3 seconds to 3 seconds. And yes, you can be asked to represent things in terms of negative time. I know that's weird, but it happens. Okay, now, the first thing we're probably going to want to do is figure out what the points are during those times, right? Okay, so we know that this is our position equation. And what was our velocity equation that we found, you guys? Negative 3t squared plus what? And that's meters per second. Okay. And we're doing the time interval from -3 all the way to 3. So we're going to make two things. I'm going to make something for time and position, and we'll have one for time and velocity. So we're going to go -3, -2, -1, 0, 1, 2, 3. -3, -2, -1, 0, 1, 2, 3. All right. Work with yourself or a buddy to fill in all of those values. All right, so let's start going ahead and getting the values up here, and we'll start off the class tomorrow with making the graphs together. But let's go ahead and just make sure everybody has the values before we leave. Sound good? So what did we get for our position at -3 seconds? What? 18? Okay, what about at -2?
2.
At -1?
-2.
At 0?
0.
Okay, it should be 0 because 0 and 0. What about at 1?
2.
At 2?
-2.
And at 3?
-18.
Okay, so we've got 18, 2, -2, 0, 2, -2, 18. Everybody agree with those? Okay, so what about our velocities? What did we get at -3? At -2? At -1?
0.
At 0?
3.
At 1?
0.
At 2?
-9.
And at 3?
-24.
You guys got really good at speaking in unison for the velocities. Okay, so tomorrow we're going to start off drawing these graphs, and then I will have a derivative practice sheet for you guys to work on. We'll do the first few together, and then I'll set you off to get some practice in with your friends and everything, okay?